last week we left a couple examples here of using the heat capacity equation. Q equals mc delta T, Q equals mcat. Just actually, let's rehash sort of what heat capacity is. Where's the best example here? Well, definition of heat capacity is the amount of heat or thermal energy, heat energy, not temperature. You've got to separate temperature and heat in your mind. They're two separate things. Related, but they're separate things. So it's the amount of heat energy required to change the temperature of a given amount of substance by 1 degree C. So one of the things that has a really high heat capacity is water. So it takes a lot of energy to warm water up. That's why it takes so long to boil water. Alternatively, if you have something, and we've got some heat capacities over here, if you took something like a copper pan and you wanted to heat up a copper pan, it's going to require more than 10 times less energy to heat up the copper than it is the water. So actually, let me do a little demonstration, a little mathematical demonstration. Let's say that we have a copper pan. Let's say it weighs 1,000 grams. So this is the Q equals mc delta T. I'm going to spread those out. So if we want to know how much energy it's going to take to heat up that copper pan from room temperature to 100 degrees C, we just plug in the mass of the copper pan, and then we use the heat capacity for copper. So that's 0.385, and that's in units of joules per gram degree C. And then that's multiplied by the mass, and then multiplied by delta T. And delta T is going to be our T final minus T initial. So whatever our ending temperature is minus the starting temperature. So we're going to go up to 100 degrees C, and we're going to start at, I'm just going to call it 17.0 degrees C. Sorry, running out of space here. So you could just, for this equation, as long as you know how much the thing weighs, the mass in grams, you know what its heat capacity is, which the heat capacity, well, in today's lab, you're going to do an experiment to figure out the heat capacity of a metal. Most of the time, you'll just look it up. So you'll go to a table. The heat capacity of this thing is, like for copper, 0.385. And you'll say you'll say, I want to heat it up from some temperature to another temperature, or I want to cool it down from some temperature to another temperature. And then you just multiply those together. So this will be 1,000 times 0.385 times 100 minus 17. So that's going to take a pretty solid amount of energy. It's going to be 31,955 joules. Now, what if we wanted to heat up water from room temperature to 100 degrees C, which is boiling, right? If you want to boil water. And 1,000 grams is about a liter of water. So maybe what you would use to make some mac and cheese. So still 1,000 grams. That doesn't change. But what does change is we use the heat capacity for water, which is 4.184. That's still joules per gram degree C. And we're still going to use this same difference in temperature, because we're going to heat it up to the same temperature. So when we say we're heating something up, we're adding heat, thermal energy to that thing. That's what increases the temperature. So if I take this, 1,000 now, times 4.184, times 100 minus 17, that is going to take not 31,000, but 347,272 joules. Right? So 10 times more energy to take water, the same mass of water, from 17 to 100 degrees C. That's what heat capacity is. It's that you need all of this extra, well, not extra energy, you need just so much more energy for this thing or less energy for other things. This is why if you left a pan of water out in the sun, the water's not going to get very hot. But if you leave like a piece of metal out in the sun, it gets really hot really fast. And if you were to go out and touch it, it's going to feel really hot. Okay. So let's apply this to another problem, though. Let's say we have a lead fishing weight, rises from 26 degrees C to 38 degrees C as it absorbs 11.3 joules of heat. What is the mass of the fishing weight in grams? So with the heat capacity equation, we can substitute in, if we can substitute in all the numbers except for one, we can solve for that one thing in the equation. So let's write in what we're given here. We have a lead fishing weight, that's important, that it's made of lead. And then we're given, right, this is where you gotta interpret the word problem a little bit. It's rising from 26 degrees C to 38 degrees C. So it's saying that we're starting at 36. We're gonna be starting at 26, ending at 38. So our T initial is equal to 26 degrees C. Our T final is equal to 38 degrees C. And then we're told that it absorbs 11.3 joules of heat. Again, heat is the energy. Temperature is the measure of the average energy inside of a substance. So our Q is going to be that 11.3 joules of heat. And then we're asked, what is the mass of the fishing weight in grams? And we're also going to need the heat capacity, which is C, of lead, which I do not have memorized, 0.128. And I'll give you the heat capacities that you need on exams. All right, so what's our equation?
Q equals M delta T.
Q equals MC.
Oh yeah, MC delta T.
Yeah, MCAT. And then you got to remember there's sort of a hidden sub-equation in here. That delta T means T final minus T initial. So we can even rewrite this as Q equals MC, and then plug in here T final minus T initial. So you could be given a problem where it just tells you the change in temperature is some amount. And then you just replace the whole delta T with that number, because it's already done the final minus initial for you. In this case, though, we have both temperatures. So now we're just going to plug in all of the numbers that we do have. So it's going to be 11.3 joules equals mass, which we don't have, right? One variable we don't have, C, and that's going to be times 128 joules per gram degree C. And then 38 is our T final minus 26 degrees C as our T initial. And now we algebra. So you always start with whatever's in parentheses. So we can do 38 minus 26. So that'll give us 12 times 0.128 times M, 11.3 joules. What should we do next? There's a few things that we could do.
Try to get M by itself.
Right, yeah. The goal here, being to get M by itself. Yeah, we can do it all at the same time. Or we could multiply, because these are two numbers without variables, we can just multiply those together first. So this a little bit comes down to whatever you're comfortable with. So I'm going to do the 0.128 times 12. So now this is going to be 1.536. And then our units here, we can even look at and say, oh, the degree C there will cancel out. Because this is 1 over degree C. This is degree C. So we'll be left with joules per gram times mass equals 11.3 joules. And then we divide both sides by 1.5, sorry, that's the whole thing, 36 joules per gram, 1.536 joules per gram. So 11.3 divided by 1.536 is going to be 7. Oops, switched the highlighter on accident. 7.3. This will actually be 2 sig figs. And I'll run through that here in a second. 7.4 grams equals the mass. Because there's a fixed relationship between the amount of mass, the change in temperature, and the amount of energy that's required. So that if we have more mass, it's going to take proportionally more energy. Right, so if we had twice the mass, it would take twice as much energy. If we increase the temperature by twice as much, it's going to take twice the energy. Those things scale, it's a directly proportional relationship. You don't have to think about it like that, but plugging it into this equation, that's what you're doing. You're figuring out that change. Oh yeah, I said I was going to run through the, yeah, okay. So for the sig figs of this, you got to pay attention to the step-by-step because we have a subtraction as a part of our other multiplication and division that we're doing. And that's the first step. So from these two, how many sig figs are we going to have? 2. Yeah, just 2. So this is going to be 2 sig figs. Sometimes you'll get 2 numbers that subtract. So if this had been 38.0 and 26.0, that would be 3 sig figs. And we're keeping the smallest number of decimal places because it's subtraction. But here, we don't have any decimal places. So it's going to be 12, and that's 2 sig figs. So when we multiply 12 by 0.128, how many sig figs do we have? Still 2. Yeah, because 12 only has 2 sig figs. So that means that, can I use a different? Oh, here, I'll highlight them. So that means this only has 2 sig figs. So when we divide both sides by that number, which only has 2 sig figs, our final result will only have 2 sig figs. So this is one of the places where you have to work through it step by step. Also, please, at any point, let me know if the colors that I see on here, way different than what the projector does. It's like that red is way lighter on here. So if you can't read something because I highlight it in a color that shows up really poorly on the projector, just let me know. Happy to change those. All right, does that make sense? We're going through this in a lot of depth because you're going to need it today. Monday night's lab, struggled. The experiment is not super long. Some of the math is. It's not super complicated, but gets kind of algebra heavy. All right, so if you have a 328 gram sample of water, absorbs 5.78 times 10 to the 3 joules of heat. Find the change in temperature for the water if the water is initially at 25 degrees C. So what is its final temperature? Where should we start on this problem? Givens. Yeah, let's write the givens down. So we've got a mass, 328 grams. We've got, what is this one going to be? Q. So the amount of joules is always going to be Q. And then what else are we given?
T initial.
Yeah, T initial. And then we want to find T final. What other piece of information do we need? Yeah, specific heat of water, right? So we need the specific heat of the compound that we're interested in. So that's going to be C. And that one I do have memorized, 4.184. That's still joules per gram degree C. So actually, so we're going to have Q equals M C delta T. I'm going to start all the way at the top. Right, and then we can break that. Oops. Let's open up or write out what that delta T is. T final minus T initial. And now we can start plugging numbers in because we have, well, we've listed them all out here, right? So we know what our givens are, and then we can sort of go from there, right? If we need to find more, if we haven't filled in all of the variables, maybe there's a way that we can figure it out through another equation or from some interpretation of the information that we're given. If we have every variable filled in except for one, then we can solve for that one. So we have the joules, we have a mass in grams. We have 4.184, that's joules per gram degree C, times our T final, which we're looking for, then minus 25.0 degrees C. Yeah. Yeah. If there are ever variables that are just next to each other in an equation, those are going to be multiplied together. Yeah. If it's going to be added or subtracted, that'll be written out explicitly, or division. That's a great question. Some I gloss over. So yeah, everything over here is being multiplied together. Now, my advice for solving these type of problems, collapse and multiply together all of the numbers that you can, right? Get those simplified as much as possible. And so we'll go through those steps and I'll show you exactly what I mean by that. So first example here is that we can multiply these two numbers together because these two are being multiplied by everything that's in here. So it's going to make things simpler for us to do that. And we'll do 328 times 4.184. So this is 1,372. Now, I think just to make your lives easier, if you can keep everything in your calculator and keep absolutely all of the decimal places, you should do that. If you don't know how to manipulate your calculator and use it to do that, just make sure you get like 5 sig figs at least. 6 sig figs. You don't have to write down all 10 or 11 numbers or however many this will display. That will avoid the vast majority of the rounding error. Now in this case, that's not so much that it's a burden to write it all down, so I'm writing it all down. But okay, so we collapse those. What are the units of that going to be? Joules per what? Yeah. Joules per degree C. Now that is still multiplied by 25, or T final minus 25.0 degrees C. And on the other side, still 5.78 times 10 to the 3 joules. Everybody tracking so far? Ask questions if you got them. So now we can still simplify some numbers by multiplying or dividing them, because this is being multiplied by all of this. That means that we can divide both sides by that number and remove it from that parentheses. Get it over to the other side, because our ultimate goal here is to get t final by itself. There is one thing here, though, that you're going to have to do tonight. If you can't move this to the other side, then you would have to, and the reason just trust me tonight that you won't be able to. What I want to mention, though, is the other thing that you can do here is you can distribute this to both of the numbers in the parentheses. So since these numbers in here are being subtracted, we can't just multiply it by one of them. It's being multiplied by both of those. So then we would get, 1,372 TF minus whatever 25 times this number is. And you could move forward from there. It's easier here to take this and move it to the other side first. So we'll now divide both sides by 1372.352 joules per degree C. Joules per degree C. All right, because now these will, so anything divided by itself is 1. So then we're going to do 5.78 times 10 to the 3. Very important that you use that scientific notation. Divided by our 1,372. So now we've got 4.2. So here's an example of where your calculator is going to spit out a lot of digits, and we're just going to write down 5 of them. That should be enough to avoid rounding error. What are our units here now? They'll be degree C. It's a little harder to see when you get fractions divided by, or when you get something divided by a fraction. Actually, let me just do this super quick on the board. If you get like this, right, it's joules over degree C. That's really hard to deal with mentally. So you can rewrite it as joules divided by joules over degree C. And then this, if we take this fraction and flip it, we can change this to multiplication. So now it's joules times degree C over joules. So highly recommend. When I discovered this, it was game changing. Because any of these situations where you get a fraction like this, my brain does not know what to do with that. So just change it into this form, flip the fraction, and then you can multiply, and now it looks like all of our unit conversions. You can clearly see that we get joules divided by joules, and degree C is all that's left. So that's what's happening here. Now we've got, and because we have nothing now being multiplied by this TF minus 25.0, we can get rid of those parentheses. Because all they were telling us is the thing that's being multiplied in front is being multiplied by everything inside of this, inside of these parentheses. So now this is TF minus 25.0 degrees C. So how do we get TF by itself? Yep, add 25.0 to both sides, because it's a negative. Right, it's being subtracted here, so it's a negative 25. And then plus 25.0 degrees C over here. So this will be 29.2117 degrees C equals T final. How many sig figs do we have? We'll have 3 sig figs, and we'll have 1 decimal place, yeah. So because we saved this addition till the very, very end, that will be, the result of this last number will be based on how many, or the smallest number of decimal places. It's going to be 29.2 degrees C. That would be the final answer. Cool. This is mostly an algebra lesson, right? Just talking about how to rearrange all this stuff. Yeah. Yep.
Why wouldn't, I mean, so for the 4.2 to 117, you could keep, like the whole number instead of rounding it, like, because I thought when you had multiplication and addition, when you finish like all the multiplication and division, you like round it that way, and then, sorry if that doesn't make sense. Like you round the intermediate answer,
Ah.
and then,
Yeah. No, so you don't round the intermediate answers. So that's why, like, I use, I know you weren't here for those first lectures. If we want to track, though, how many sig figs we're keeping, I usually underline, if there's space to underline them, which digits are significant. So, like, we started here with this times this. So the result of that would have how many sig figs? 3. So we underline the first 3 numbers. I usually go back and do this after I've worked the whole problem out, so I'm not thinking about that on top of the other thing. So if this only has 3 sig figs, then when we divide this by this, well, both of those will only have still 3 sig figs. So then the result here is those are the 3 significant.
but you still
You keep all of them.
until the end.
Yeah.
Can you determine the sig figs by the column on the top? You know, has all those numbers up there?
Not really.
Why wouldn't it just be like, oh, there's 3?
The only reason that you can't is because this equation has addition, or well, it has subtraction in it. So depending on where that subtraction happens, you need to factor it into your sig figs at different places. And you're probably not going to know, and I wouldn't know probably from just looking at it without thinking really, really hard about it. Harder than is necessary beforehand to try and figure out where that subtraction is going to happen and how it's going to change the total number of sig figs.
Well, because you put all the given, you wrote it down.
Yeah.
And you wrote all the given, which are really the same numbers up there,
Yes.
which are where you got the sig figs. Because there's 328 and there's 25.0, so that's why there's 3, no? And then 5.70, that's 3, 2.
In this one, it does end up working out that way, but if this, there are places where it doesn't work out like that, and so I'd recommend going through and actually tracking it. I cannot think of an example off of the top of my head, but there are situations, especially with addition and subtraction, where kind of weird stuff happens. So, actually, here's an example. If we had, let me just insert another page real quick. Oh no, that is the last page. So, what just happened? Okay, so if we had if we'd been given a temperature change that went from, let's say it's 25.0, would be, let's call that our T initial, and our T final is 25.5. And then I'll just throw in a mass, let's call it 111 grams. It'll be for water, so it's going to be 4.184. And if we take our equation for Q and we plug in these numbers, final minus initial is going to be 25.5 minus 25.0. So, right, the minimum number of sig figs we have in our givens is 3.
Yeah.
But when we subtract this, how many sig figs does that end up with? Just 1 sig fig. because we keep the smallest number of decimal places. So now when we multiply this by everything else, we're only going to have one sig fig for our final answer.
So then we get the sig fig depending on the T initial and T final. That's where we get the sig fig, whatever answer we get.
I think if you want to use that as a rule of thumb, that might be okay. But I would still go through and, based on the math that happens, figure out how many sig figs you're going to have. For problems where it's just multiplication or division, then yes, you can look at your initial sig figs and say the smallest number of those sig figs is going to be my final answer's number of sig figs. But because we have this addition or subtraction in, it is very likely, but I can't say for sure that it's always going to be whatever the T final minus T initial is. Does that make sense? I don't want to say a blanket statement, yes, it's always that. Because only the Sith deal in absolutes, which is an absolute. But I think most of the time that's going to work out for you, if you think about it like that. I can't think of examples where it wouldn't. Doesn't mean they don't exist.
The problem before that, though, I didn't understand why you added the 25.
Oh, I added the 25 to both sides?
Yeah.
I did that because this is minus 25. So it means it's like plus a negative 25.
So you would need to like zero it out.
I'm zeroing it out, yeah. So if I add it to both sides, then it becomes, this would become 0. So like if I rewrote this as, right, just T final minus 25.0 degrees C plus 25 degrees, or 0.0, right? That adds up to 0. So you would just have TF. So if this had been, well, that if it's the T initial here, this is always going to be negative because it's final minus initial. Still on tracking?
I'll get it after a while.
Okay.
So, but then you would do it to the other side because you don't want to have like a lopsided equation.
Yeah.
That's the way I look at it. I don't know if that helps or not.
So it's kind of like we're adding it to, like, the equals is a scale, or is like the middle of a scale. So we can't just add 25 to one side because now it's not equal anymore. So if we can add it, though, to both sides, and those scales are still equal. We're just putting more on both sides. And then for dividing or multiplying, we're kind of doing the same thing. We just have to do it to both sides. And the number that we multiply or divide on both sides is just the one that's convenient for canceling out the units on the sides where we don't want it, or the numbers, right? So the same reason that we add 25 is the same reason that we divided this 1372. You can do more examples of that. The one thing that I want to put this into your minds, this concept into your minds, is what if we have, let's say we have a metal cube, and let's just say it's made out of lead. So we have this lead cube, and let's say we take that cube and we heat it up, get it really hot. So we get it all the way up to 100 degrees C. And now we take that lead cube and a glass of water. Let's say, or I should give you a mass. So T initial for the lead cube is that. And the mass of the lead cube is, let's call it 100 grams. So you've got this 100-gram lead cube. It's 100 degrees C. We take that and we drop it into a glass of cold water. So now we've got a glass of water. It's a really weird shaped glass. And let's say that there's, the mass in here is going to be 100 grams of water. And its T initial is, let's call it 20 degrees C. What's going to happen to the water? It's going to rise in temperature. By how much? Not by 100 C, but by how much energy the lead cube has and how much it dumps into the water. So this lead cube has some amount of energy Q. And when we put that lead cube into the water, all of its heat is going to get transferred into the water. And then, yeah, it might make a little bit of steam, but that water temperature of the water is going to rise, and it's going to rise by that Q from the metal. So, so C for the metal is going to be 0.128. And let's say that I'm just kind of coming up with this off the top of my head. Let's say that we add this cube in and we want to know what the final temperature is going to be. This is going to be the problem that you're going to have to do tonight. So if we put this in, yeah, what temperature are these going to come to? So the core concept here, though, is that we have some Q from the metal, because as the cube goes in, it's going to cool down. As it cools down, it's going to be giving that up energy into the water. The water's going to warm up, and they're going to meet somewhere in the middle, right? Because the cube's not going to cool all the way down to the initial temperature of the water, and the water's not going to warm up all the way to the initial temperature of the metal, but it'll be somewhere in between. So that energy from the metal will be negative Q. So it's losing energy. That is going to be equal to the energy that's gained by the water. So any energy lost by the metal is being given to the water. And our C for water is going to be, this is a little bit different from the problem tonight, but that's okay. And I'm not going to work out this whole thing right now, but keep this idea in mind. So if we can calculate Q for the metal, we're missing one thing. So Q metal is going to be equal to the mass of the metal times C times the change in temperature, but we don't know what that final temperature is. And then Q for the water is going to be the same, but it's now the mass of the water, C for the water, and the change in temperature for the water. And so if we want to find T final, that T final for the metal and the water is going to be the same. Because once it's in there, they're going to meet in the middle. And once they have the same amount, once they have the same temperature, they're not going to transfer any heat to or from each other anymore. So we can take this equation for Q of the metal, plug it in here. You take this equation for Q of the water, plug it in here, and solve for T final. And that'll tell you what temperature they'll meet at. Exactly.
Both of them should have the same exact answer.
They'll both have the same final temperature. So just remember, heat is being transferred from one place to another. The amount of heat lost by one thing, we're going to do this in like styrofoam cups. The heat lost from the one thing in the styrofoam cup is the heat gained by the other. Okay. So that'll do it for